Oh, please go ahead.
Yeah. I wish to thank the organizers for giving me this opportunity to speak at this well-known conference, and also for taking like a lot of effort goes into organization. So I would thank Mel Nathanson, Kevin O'Brien, and Stephen Miller, and also there are others, I'm sure. All right, so let me start. This talk is dedicated to the memory of Wolfgang Moens, who unfortunately left us in 2022. So I will speak about asymptotic approximate groups in virtually nilpotent groups. So, first some basics. So like well-known basics. So for a subset A of an abelian group, we will define the Minkowski sum set, which will be the usual sum set which we take in additive combinatorics, and we will also need the product set. So again, the same thing, but with products and which are not necessarily commutative. So starting point will be theorem of Nathanson. Actually, two results of Nathanson. One was from 2016, I think, and the other 2018. So he defines something called an asymptotic approximate group. We will come to a definition later. But he showed that every non-empty finite subset of the integers is an asymptotic approximate group. And then later he extended it to cover all abelian groups. So any non-empty subset of an abelian group is also an asymptotic approximate group. And he also showed in the second paper that this fact doesn't hold true for all groups. For instance, in free groups, it's not true. So before going into asymptotic approximate group, let us recall what is an approximate group. So the first standard definition of an approximate group was given by Tao in 2008, around 2008. So a finite set in a group is a K-approximate group. If you have the identity in the set is symmetric. And when you take the product of A with itself, it should be contained in X times A for some symmetric set X with the size of X less than equal to K. So this theory becomes interesting when K is independent of A, because otherwise any set is like if you can increase A, then any set becomes an approximate group. Like if K is allowed to depend on A, size of A. So why is it an approximate group? So you can see clearly that if K is equal to 1, then this is exactly the definition of a subgroup. And so if you perturb K a little bit, so if you take K equal to 1 plus epsilon, then it remains very close to being a subgroup. And thus multiplying A by itself produces only boundedly many translates of A, in the sense that A behaves approximately like a finite subgroup. And obviously, like this theory, like even though it was proposed by, like the definition was proposed by Tao in 2008, it had been studied before in the context of additive combinatorics since the 1960s, celebrated theorem of Freiman, which essentially was one of the first instances when approximate groups were studied in the context of integers. So Freiman's theorems like informally states that finite sets which have small sum set have some algebraic structure. And then Tao made it more abstract, and then like he gave a general framework for small product sets in non-abelian groups. And Brouillard, Green, Tao, like they classified approximate groups by saying that approximate groups are essentially controlled by virtually nilpotent algebraic models. And why are they important? So they have found a lot of applications since the last 15-20 years at least. So for instance, Freeman type theorems in general abelian groups by Green, Ruja. I cannot list all of them, but some of them would be like, so then there was the product growth. So product theorems for finite simple groups of bounded Lie rank, which resolved a conjecture of Baba in the bounded Lie rank case. The conjecture is still open for the unbounded case. So these would be teams of researchers like Brouillard, Green, Tao, Paiba, Szabo. Then there were initial work on SL2FP, which basically was initial breakthrough by Helfgott. So this would be around 2007. Then they also found application in construction of expanders and super strong approximation for linear groups, Bourgan, Gambourg, and some subsequent works. They gave new proofs of theorems of Gromov. So for instance, structure and quantity approaches to Gromov's theorem, groups with polynomial growth are virtually nilpotent. And the general principle of all of these use approximate groups in some form or other. So the general principle would be like small growth of a finite set will force some. Sorry, is there a question? No. No. Okay, so small growth of a finite set which will force some strong algebraic structure. And so what is the connection with this talk? So we will study a large scale version of the same principle. So, so recall that in the previous case, we had a square contained x times a. Here we will take something like a to the power rh, which will be contained in xh times a to the power h, where xh will be, the size of xh will be bounded. Okay, it will be independent of h. And so essentially, you can think of it as instead of this 2 before the a square, you can think of it as a to the power r, and you can look at it as a to the power h to the power r, which is contained in x to the power h a to the power h, and h tends to infinity. Okay, so this is the like setting. And so, okay, so let's come to definition of the asymptotic approximate groups. So fix R and L bigger than equal to 2 to make it interesting. A non-empty set A in G is an asymptotic RL approximate group if there is some H0 such that for every H bigger than equal to H0, there is some XH in G which satisfies the following. So the size of XH is less than equal to L, and the a to the power RH is contained in XH a to the power H. So again, L here depends on A and R. It is independent of H. So essentially, it's the same thing as approximate groups, but after some finite steps. So a to the power H becomes R approximate group once you cross the threshold H0. So there will exist a finite H0. So this is how I like to look at it. And so and Nathanson showed the following. So if A is a finite subset of an abelian group with the size of A equal to K, then for every fixed R, there exists an explicit L and H0 such that if this here I'm just using a D2 notation. So a to the power RH is in XH times a to the power H. And so any finite set in an abelian group satisfies this condition. Okay. And thus every finite subset of an abelian group is an asymptotic approximate group. And he explicitly gave some bounds on L, which were later improved. And so all right, so then so all this was in the abelian case. So why do we consider virtual nilpotent groups here? So the thing would be, together with Wolfgang Moens in 2020, we wrote the paper, I think, when we were in Vienna. So we showed the following. So first of all, our motivation was to improve the constants on the L here in Nathanson's result. So we gave a different proof, a geometric covering proof, and it improved the constants a bit. Then we are also looking at what sort of infinite sets will also satisfy this property. Because so this property is quite natural, and so what sort of infinite sets? So Nathanson had showed that all finite sets satisfy this property in abelian groups. So we're looking at in abelian groups what sort of infinite sets will satisfy, and so a natural candidate was semilinear sets. So semilinear sets, just to recall, is a finite union of arithmetic progressions. It can be d-dimensional arithmetic progressions, generalized arithmetic progressions, and which is quite intuitive, right? Because you expect that, okay, so when your arithmetic progressions, when you're adding, when you're summing them up more and more, they will, since they already have structure, so structure gets added to itself. So this was, so this set of sets, they also satisfy this property. And we are also able to show that if a finite set A in an arbitrary group is an asymptotic RL approximate group, then the subgroup generated by A will be virtually nilpotent. So, and for this, we use uniform covering, and we got to polynomial growth, and then basically polynomial growth, which will imply virtual nilpotent. So here we are using Gromov's theorem, which is a strong, obviously strong result. And so, so what does that mean? So that means that Nathanson's that result that that this phenomena does not occur, that any finite subset is an asymptotic approximate group does not occur, in all groups, and he gave the example in free groups, actually holds earlier. So basically, you can go to solvable groups and you can find, or even polycyclic groups which are bigger than nilpotent, virtual nilpotent. So in there, you can find finite subsets which do not satisfy this property. And so the next question is quite natural. So virtual nilpotence is therefore necessary for a finite asymptotic approximate group. To what extent is it also sufficient? More precisely, which finite or infinite subsets of a virtual nilpotent group are asymptotic approximate groups? And so this was the motivation why we are like in the context of virtual nilpotent groups now. And so recently, like a few months ago, so I was thinking about this problem, and so what we could show is that so if G is a virtual nilpotent group, then if you take any finite non-empty symmetric set, then it will be an asymptotic approximate group. Yeah? And the same conclusion will hold for finite A, which semi-group generates A, with the subgroup. Okay, so by semi-group generation, I mean exactly this. So the a to the power h, it will cover the whole space. So essentially, like after the balls, after a certain amount, like after a certain distance, it will contain also the inverses. Okay. And we also were able to show this, that there is an infinite set analog for this semi-linear sets in the context of virtually nilpotent groups. So these are not exactly, so I would say an analog of arithmetic progressions in case of nilpotent groups would be nil progressions. But in here we need a bit more structure. So there is an infinite set analog where, so basically, if we take A to be Fm, where M is a sub semi group and F normalizes M, so we need this condition that F normalizes M, then these sort of sets will also be asymptotic approximate group. And also there is an open question, which is that what happens, so if you can see here in the main result, I do not say anything about like general asymmetric subset, which was shown also in Nathanson's work. If you take even asymmetric subset in abelian groups, it will also be a finite asymmetric subset in abelian groups. It will also be a virtual nilpotent group. So I don't know yet, what happens for an arbitrary finite asymmetric subset of a virtual nilpotent group, because the proof method that we used here depends on the Bas-Givars theorem. And so, and there we always deal with basically metric. So the word ball metrics, and yeah, so those are symmetric sets. Or yeah. So right. So the ingredients which we will use. So I will just go. I will not go in details in all the proofs, but I will just go through the steps which we use. So right. So the ingredients. So two ingredients which we use are the Bas-Givars theorem, which says that in case of finitely generated virtual nilpotent groups, if you take a symmetric generating set, then basically the word balls of size at most n, they are bounded by two, like C1 n to the power d and C2 n to the power d. So they lie the sizes of these balls. There exist two constants which basically bound them. Okay, and this integer d is the growth degree of gamma and the group. And we will also use the classical Ruzha covering lemma from additive combinatorics. So if you have like two finite sets, EF, non-empty finite sets, and suppose the cardinality of EF is less than or equal to k times the size of F, then there will exist an X in E with the size of X less than or equal to K, such that E is contained in some translates of F inverse, X, yeah, so X, F inverse. Okay. So how will we use them? So essentially, so what we will do is first we will derive a proposition. So the proposition will be that, all right, so the proposition will be that the word ball, so if you fix an R0 and a theta, So then there will exist an L which is less than infinity, such that for every sufficiently large H, the word balls of size at most R0 times H will be contained in some YH, the word ball of size theta H. And this essentially follows from the fact that when you take the ratio of these two word balls, then you can actually bound this by, you can use Bas-Givers to bound this by this quantity, the C2C1, and this quantity. And this is constant, right? Because this is some constant. And then once you have this bound, so EF by F, so in here E will be, the word ball of in RH, size RH, F will be the word ball size QH. And then basically after that, you can apply the Ruja covering lemma to get the result. Okay. And so the Bas-Giver is here, and then the Ruja covering lemma to bound. And once you have that proposition, so it's just a one line. So if you take a virtual nilpotent group, we know that it satisfies this Bas-Giver's condition. And then you just translate, like what we wrote in the proposition to the growth of these sets. Okay. So this is so this is just one line, and in here, so that's why we are using the symmetric sets in that form, because of symmetric sets we could we could use Bas-Givers, otherwise it will be for asymmetric sets it's not known. And and this can be generalized a bit, so to cover some types of asymmetric sets. Basically, imagine that like initially, suppose we have an asymmetric set, but suppose some finite power, after some finite power, we get some inverses. So in that case, like again we can apply this. So for some asymmetric sets we can do this, but not for the general case. Okay. And then a non-abelian, so semilinear analog of this of the one which we obtained for the semilinear sets in case of the abelian case would be that you take sub-semi group M, can be infinite, and suppose you take a set F, which is in the normalizer. Can take it finite and non-empty. The important thing is that F should itself be asymptotic approximate group, and then it is so one can obtain that if I take F times M, this will also be an asymptotic approximate group. You don't need F to be finite and non-empty. What you essentially need is that F itself should be asymptotic approximate group. So if F is symmetric and semi-group generates F, so this implies there is a asymptotic approximate group, then Fm is an asymptotic approximate group. But then one might think that, okay, so can we generalize it a bit more? Like instead of F in the normalizer, can we have that that we don't put any condition of F on F? But that is actually that fact exactly is not true. That if we don't put some sort of normalization condition is necessary. So, and this is true even in the most simplest of the virtual nilpotent groups. So suppose we take the Heisenberg group and just take this set A. This is an infinite set, xy to the power n. This represents an arithmetic progression in case of, like if we translate it to abelian case, it will represent sort of arithmetic progression because it's just the n which is increasing. And if you compute a to the power rh, you will see that a to the power rh or a to the power h, you will see that these products they give this sort of form, and basically you can show it's like a one-page proof that you can show that these won't be asymptotic approximate group. So basically, A won't be an asymptotic approximate group in this case. And that is because of the third term, like that blows up quite fast. And all right, so what is the crux of all this discussion? So basically, for a finitely generated group, the following are equivalent. So then G is virtually nilpotent. every finite non-empty symmetric subset of G is an asymptotic approximate group, and some finite symmetric generating set S containing the identity is asymptotic RL approximate group for some R. Okay, and so one can also extend it to some homomorphic images, and also something called bounded thickenings. So these are in the article. Right. So now I wish to just discuss that. So we raised an open question before, that what happens if I don't give any condition on this S. Instead of symmetricity, I just take any set S. It can be asymmetric set. So in abelian group, every finite set works. For example, in Z, if you take A to be 0, 1, then HA is this set, and this is one-sided. It's not asymmetric, and RHA is covered by R translates of HA. And so the open question is, if A is an arbitrary finite asymmetric subset of a virtual nilpotent group, must that exist for every fixed R? This XH, such that XH is independent of H. The size of XH is independent of H. It only depends on the A and R. And the previous proof no longer applies. So A to the power H need not be a symmetric word ball or contain one of radius comparable to H. And basically the arguments that had been used previously were mostly about the geometric coverings, these sort of arguments, and so one possible way. I'm not saying that it has been completely done. It has not been done. One possible way can be to study the large scale shape of A to the power H. And to see whether that can replace this missing word ball. And so, right. So for instance, Pansu in 1983, he studied large word balls in nilpotent groups, and he showed that if we look at these discrete balls in nilpotent groups from far away. So from far away, which we will mean that basically you do some normalization on the word metric, and then you look at the the growth of these balls. And so Pansu's theorem, the informal version is that so in here, if you take this large discrete ball, it looks like this. These are the points. This is the center, and these grow like this. And but the continuous limit shape will be something like this convex body. Okay, a fixed compact unit ball. And so one way might be, I'm not saying that because I did not look at very deeply, but one way might be to use this sort of geometry to argue directly that asymmetric sets can be asymptotic approximate groups in nilpotent groups. This is because, Pansu's original work was for symmetric, symmetric generating sets. I'll just look at what time. Okay, so I have 2 minutes. While Brouillard extended it to cover limit shape theory, not just from nilpotent groups, but to locally compact groups of polynomial growth. And he also remarked that symmetry of the metric is assumed mainly for simplicity, and that much of the theory should extend without it. So this suggests to adapting an asymmetric version of Brouillard's approach to the sets A to the power H. But there is a lot of work to be done because, for instance, one needs the convergence of the rescale sets to a compact directed limit shape and some sort of interior point result. And I started to look at these two papers, but unfortunately, the Pansu's paper is 30 pages long and Brouillard's paper is 60 pages long, and so it's if one has to redo the theory with asymmetry also taking into account, so one probably has to do all the steps, and so that is and right. So this is still open, what happens with general asymmetric set. All right. And so some of the takeaways will be like essentially polynomial growth. It gives a uniform covering theorem for word balls. And a linear size inner symmetric ball, it will transfer that covering theorem to the powers. And symmetry and positive semigroup generation will guarantee such an inner ball. And for infinite sets, normalization will give this identity, and which will help us to show that these sort of sets are also asymptotic approximate groups. And the Heisenberg counterexample, it shows that uncontrolled commutators can create central drift and destroy finite covering. And an asymmetry result will still need further inputs, possibly from Pansy-Bruyat style limit shape arguments. And that actually finishes my talk. So thank you for listening. If you have any questions.
Any questions for Arindam? If not, we thank the speaker again for a very, very nice talk.
Thank you.
And the next